So here is an example. Let's talk about 4 factors. We're talking about a half fraction, so we're talking about a 2 to the 4 minus 1 fractional factorial. I have factors A, B, C, and D. To follow this prescription, I'm going to look at 3 factors and write out plus and minus signs specifying the 8 different combinations of levels of those 3 factors. I'm then going to multiply those signs together and use them to specify levels of factor D, this last factor. So here's how that proceeds. In this first row, I've got minus, minus, minus. Don't know why some of these things are dropped. I know those things are in the files, but they just didn't copy over to this PDF. What I've got here on the left side of this thing is, in truth table fashion, all 8 combinations of levels of factors A, B, and C. If I multiply together along this first row 3 minus 1s, I'm going to get another minus 1. If I multiply across the second row a plus 1 and 2 minus 1s, I'm going to get a plus 1. If I multiply along the fourth row here, 2 plus signs and a minus sign, 2 plus 1s and a minus 1, I'm going to get a minus 1, and so on. And so the point here is that I've made up a column that is the product of the values in the first 3 columns, and these are what I use to choose levels of factor D. So we're talking about a half fraction of the 2 to the 4th. 4 factors, A, B, C, and D. How do I set levels for D? I use products of signs for A, B, and C. And if I look across this first row, that tells me what? It says one setup of the experiment will be for A low, B low, C low, and then D low. That's a combination that in this special 2 to the P factorial notation we call combination 1. The second row of the table says another way that we will collect data is for A high, B and C low, D high. Well, in this special naming convention for 2 to the P factorials, that is the combination AD, and so on, all the way down to this last row, the ABCD combination. What I've got listed here are 8 out of the 2 to the 4th equals 16 possible A, B, C, D combinations. This is 8 out of 16. This is a good half fraction. Of the 2 to the 4th. This is the one that I get by following my the rules that I just laid down there. As a second example, here's another data set from a chemical study. It's a chemical study that involved as I say, 5 factors, factor A, B, C, D, and E, each at 2 levels, where the response variable was a color index for some kind of a product made by the process. If I was going to do a full factorial in this context, it would require a minimum of 32 runs of the process. There are 32 ways, that is 2 to the 5th ways, to set this process up. And what we're going to talk about is not a 2 to the 5th, but half of a 2 to the 5th. So we're going to talk about a 2 to the 5 minus 1 so-called fractional factorial. And here are the combinations that SNE actually used in his study. If you count them up, there are a total of 16 out of 32 possible combinations. In this 2 to the 5 minus 1 fractional factorial. And I'm not going to take time to write it all out now, but you can convince yourself that in fact you get these by following this standard recommendation for choosing the half fraction. By the way, if I come back to this scenario, sorry, wrong one. Well, we'll get there. This scenario, as a matter of fact, the 4 circled corners come from the standard way of choosing a half fraction. That is, if I carefully down here write out A, B, and C, minus, minus, plus, plus, minus, plus, now minus, plus, and I make a product. This would be a plus, this would be a minus, and a plus. If I use that for factor C, this is, and look across this first row, that's combination C, this is combination B, this is combination A, this is combination A, B, C, and the point is that these are the 4 circled corners on that picture.